we're going through partial differentiation. Now consider the partial derivative, just maybe f of x, comma y, is equal to x squared plus y squared. Alright, now this is our problem. We want to find the partial derivative with respect to x and the partial derivative with respect to y. Now, casual or normal notation actually is usually done with, or like this, df on dx. Just for normal, like single variable functions, right? Well, in this case, for partial derivatives, we actually do a little weird df, like this. df and dx, like this. It's a little curly bit at the top, just to symbolize that we're partially differentiating it. So we're partially differentiating f with respect to x. So what you want to do is, like normal, differentiate x, but treat every single other variable like a constant. So this y squared is just some constant. So you can just suppose like it's whatever, like say 7. Well, taking the partial derivative of this, x squared just becomes 2x because of the power rule. And then y squared is just a constant, and we know that differentiating a constant just means 0. And all we're left with is 2x. That's our partial derivative with respect to x. Now, a partial derivative with respect to y, right, similarly just switching the dx for a dy. Now it's basically the same thing, right? We're treating x as a constant now instead of y, and we're just differentiating y. So we can just suppose now x is just whatever, like 3. So derivative of x squared is just a constant, so it's 0, plus the derivative of y squared, which would be 2y. Which just nets us 0 plus 2y is 2y. Now, knowing what we know, let's maybe try a more difficult problem. So, say for example, let's just say we had f of x, y, and let's throw in maybe a third variable, z. Now this is currently our problem. Now what we want to do is we want to find the partial derivative with respect to x, with respect to y, and with respect to z, right? So let's just start off. So, and I've seen before, the notation is just this curly d. So we have df on dx, representing the partial derivative, is equal to. Now what we do is, again, as I said before, or said previously, we treat everything else as a constant besides x. So differentiating this with respect to x, we get 2x, just differentiating x. Since y cubed times sine of z is just a constant, we can keep it here. And we don't have to do anything to it. So y cubed sine of z. I'm moving on to the next term. There are no x terms in here, and this is just a constant. Derivative of this would just be 0. There's no x term in here, so this would also be 0. So we have our partial derivative with respect to x is 2xy cubed sine of z. Now taking the partial derivative with respect to y, df on dy. Now we treat everything else besides y as a constant. So differentiating y cubed would just be 3y squared, right? And since x squared sine of z is just a constant, we can just write it down like normal. Plus, now the derivative of y times z squared with respect to y, we just differentiate y, becoming 1. And then since z squared is just a constant, we can leave it here. So 1 times z squared. Plus the derivative of 3 cos y, so this would just be minus 3 sine y, as the derivative of cos is just minus sine. And now this is a partial derivative with respect to y. Now finally, we want to take our partial derivative with respect to z now. So df on dz is now equal to, now treating everything else besides z as a constant, we have the derivative of sine of z, which is cos of z, right? So we have cos of z Similarly, x squared times y cubed is now a constant, so we can just leave it here. So x squared y cubed. We have plus, now the derivative of z squared is 2z, multiplied by y, because we just leave it because it's a constant, plus the derivative of this with respect to z is just 0. Now that's our partial derivative with respect to z. Cos of z times x squared y cubed plus 2zy. And that's all.